Hello, and welcome to the Space Telescope Public Lecture Series. Today's talk, To Catch a Dancing Star, the story of extreme precision spectroscopy with Arpita Roy from the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at Space Telescope. And I always want to thank the amazing tech team that gets it set up to stream this out, Thomas Marufu and Grant Justice. I will also note that the Space Telescope Public Lecture Series will be online only until further notice. We did have somebody send in a question about why is this and when will we be back? Unfortunately, I can't give you a direct answer as when we will be back. The answer is basically whenever it's safe for 150 people to congregate in an auditorium at close distance for about 2 hours, okay? I honestly haven't been back in the office but 4 or 5 times since the start of the pandemic. And we're being kind of careful because we're now the Missions Operations Center of the James Webb Space Telescope. So I really can't tell you when we will be back, but will continue to reevaluate as things progress. You'll want to know about our upcoming lectures. Next month on March 1st, we have Hubble from space and integral field spectroscopy from the ground, seeing both the forests and the trees. And this is going to be our first lecture from across the pond, Mark Sazi of ARMA Observatory and Planetarium. On April 5th, we will have neutrino astronomy with IceCube from Marco Santander of the University of Alabama. And on May 3rd, a wonderful speaker will present a fascinating topic. I actually have to choose between a couple speakers for that, and we have not gotten that set just yet, but that will be set very, very soon. You can find out about it when it is set on our website, stsci.edu/public-lectures, where you will find links to our webcasts and also a helpful button where you can subscribe to our email list. On the website is, of course, a list of all the upcoming lectures. And if you click on any one of those lectures, you find all the details about it, including after it's been recorded, the link to the STSCI webcast, as well as the webcast on YouTube. The email that I talked about, well, the announcements are just much easiest to sign up at the website. You can also subscribe to our YouTube channel, which is youtube.com/Hubble Space Telescope, all one word. And you will get new video notices and reminders of these live events. Finally, if you have comments or questions, you can send them to us via the email address publiclecture@stsci.edu. You can also contact us via social media. We have social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute, as you can see on Facebook, Twitter, YouTube, and Instagram. I myself do a tiny, tiny amount of social media on Facebook and Twitter as Dr. Frank Summers. And now the news from the universe for February 2022. Our top story tonight, home on Lagrange, or if you actually speak French, it would be Lagrange, because we are talking about the James Webb Space Telescope, which has finally made it home at Lagrange Point 2. Now, last month, if you were paying attention, you know that astronomers got their holiday present with the launch of the James Webb Space Telescope on Christmas Day. And since then, it has been doing its unfolding on its way out to the L2 point. Let's see. So last time it was January 3rd or 4th when the sun shield had just finished deploying, okay? After that, the secondary mirror unfolds. So you can see here that the secondary mirror, which is this strut out here, that unfold. And on January 7th and 8th, the wings of the mirror, these 3 mirrors on either side, they unfolded. And by January 8th, we had a full telescope. It looked like, all the pictures we've shown of you until now, it finished its unfolding. And this was immense source of relief for us on the project. I also showed you this diagram showing Webb's path to the Lagrangian 2-point. And notice that it doesn't actually sit at the Lagrangian 2-point, it orbits around the Lagrangian 2-point. Matter of fact, the diameter of this orbit is almost the same distance as it is away from Earth. So it's a really, really big orbit, okay? They call these orbits halo orbits. And it actually takes about 6 months to go around this orbit. And in order to stay in this orbit, it has to do a little station keeping, just a little thruster bursts every 2 weeks. They plan those to be. So, it's a big giant orbit. It has to do just a tiny little bit of station keeping to keep it on this orbit. And basically, you can think of this very first orbit around the Lagrangian 2-point as the commissioning timescale. Now, you want proof that Webb is out there? I can't give you absolute proof, but I can give you a picture that taken by a group of folks who run the virtual telescope. And they tell us that tiny little dot right in there, that tiny little dot in there is the James Webb Space Telescope. Now, this was taken after the sun shield had unfolded, so Webb is actually highly reflective on its backside that faces Earth, right? Because, of course, it's blocking all the sun. So it's highly reflective there, and they can get this picture of Webb. Kind of cool. If you want to know what's next for Webb, well, during this first orbit, we're going to be doing commissioning, okay? So the first thing, mirror alignment. They've already unlocked the mirrors and moved them out of their launch positions. They're sort of, they're locked down for launch so that they don't vibrate too much, and they've been released, and now they're going to start doing focusing. All right, and focusing begins with what we call first light, the first photons that get processed by the telescope. And they chose this star, HD 84406, which is a bright star in the constellation Ursa Major. And it's actually much too bright for Webb to observe when Webb is fully focused, okay? This is a 6.5 magnitude star, and that's too bright for Webb to look at, but it actually works very well for just the initial work of getting focused, because the first images that we're going to get aren't going to be bright, crisp images. They're going to be blurry, and then they'll spend 3 months. It's going to take 3 months because you've got 18 mirrors and you've got multiple instruments spread across the focus plane, and you've got to check that the focus is perfect on every single one of those instruments through and adjust all 18 mirrors. So these tiny, tiny, tiny little adjustments, okay? So yeah, that's going to take 3 months. The other thing that's going on also, of course, is the cooling and outgassing. Now, the instruments have been kept heated, okay? They've just been heated so that as they outgas, some of the outgas things don't deposit onto the instruments themselves. For example, if water vapor outgasses and it deposits on the instrument, it could freeze and you could get ice, and that would be a bad thing. So they will start turning off those heaters. I think they've already turned off one. I'm not exactly sure. And then let the instruments passively cool. Once they figure all the outgassing that needs to occur has occurred, they'll turn them off and let them cool. And they really have to cool way, 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 way down. You're going to get to 40 Kelvin for the near infrared instruments. 40 Kelvin scale is the absolute scale. It's 273 degrees below 0 centigrade, which is like twice that, like 470 degrees below 0 Fahrenheit. And the MIRI actually has a cryocooler to get it even colder. MIRI is the mid-infrared instrument. And that cryocooler will get that down to 6 Kelvin, 6 degrees above absolute zero. And that's the kind of temperatures you want to get to do research level science in the infrared. Also, during this first orbit, they will be doing instrument checkout. They have lots of instruments, and these instruments have lots of different observing modes, and every single one of them must be put through its paces with, guide star, with sample observations out there. And so there's just, this telescope is really, really powerful and could do many, many things, but every single one of those things needs to be checked out during commissioning. That is why it's going to take 6 months. So the Associated Universities for Research in Astronomy put out this really cool graphic. All right, so it's cool to us geeks, okay? You can download it. I think they posted it on Twitter about the Webb commissioning, and you can follow all of the various things that should be happening over the course of this first orbit, this first 6 months. And you can expect that we will get actual observations released to the public starting in earliest July 4th timeframe. Okay, so that's the next 6 months of Webb, and it's a really exciting time. Okay, all right. As I gave you last week, if you want ongoing Webb info, you can go to this Where is Webb website. You can go to the NASA Webb blog, which is actually the place I go to most these days. Now that the unfolding is all happening, the NASA Webb blog has the cool information. And then when special things happen, maybe they'll be doing something special for First Light, NASA Live. Okay. So a second story today, and just a little short one because I knew Webb was going to be a long one. But Eta Carinae erupts into 3D. So these are some NASA observations of the massive star Eta Carinae. Now you'll often hear people call it Eta Carina. Okay, that's actually wrong because the correct name is Eta Carinae, but of course that's kind of funky to say, so everyone just calls it Eta Car. Okay, and Eta Car is one of the most massive stars known, and in the 1840s it had this eruption. Okay, and what it did, and you can see here invisible, is it actually blew out a small nebula. This is called the Homunculus Nebula. And Hubble has looked at it several times. And this is actually Hubble's observations in the ultraviolet and Hubble's observations in the hydrogen alpha filter. Also, the Chandra Space Telescope has observed it. And here are these X-rays, all right? And so what our team did here at Space Telescope Science Institute is take these images and turn them into three-dimensional models. So here is a small little movie of it, starting with the visible light homunculus nebula, and you can see the dumbbell shape of it, sort of the hourglass shape. And then some of that ultraviolet light spreads through the homunculus nebula. And outside of that is gas that was ejected from Eta Car that's heated up to hydrogen alpha temperatures. And then there's this X-ray gas out at the edge, which actually makes no sense because why should the highest energy stuff be the farthest away from the star? Well, I know you want to know more. So go to Hubble site or universeoflearning.org. There you will find the full videos. The full one is Eta Carinae, the great eruption of a massive star. It's a 4.5-minute video that goes through it and explains a good amount of it. And then we have this shorter one, which is about 1.5 minutes, which is just the three-dimensional models, but it goes through it much more slowly so you can watch it. What I just showed you is what we put on social media, and social media says I can't do anything more than 30 seconds. So you got the 30-second version, but the longer versions are available on our website. So let's go to our featured speaker tonight. Arpita Roy is an astronomer here at the Space Telescope Science Institute. She's been here just over a year. So like another of our speakers that I introduced, she works at STSCI, but she's never been in an office. I'm not sure she even has an office. We've hired some people that never been in the office. She came to us from a postdoc at Caltech, where she was a Millikan Fellow. And before that, she did her graduate work at Penn State. Here at Space Telescope, she is working on the James Webb Space Telescope, the near infrared spectrograph called NIRISS. And she has a good experience in a range of astronomy, building instruments, observing with those instruments, and doing the analysis of the data. She's not a specialist. And I always ask my speakers for one interesting thing about them. And what Arpita told me was that when she did her undergraduate work, she was a double major. Yeah, she did the usual geek science one, but she also has a degree in creative writing. So we have a wonderfully creative astronomer to present to you tonight. Ladies and gentlemen, Dr. Arpita Roy.
Thanks, Frank. It's a pleasure to be here today to talk to you about stars and measuring their motions, and to tell you the story of extreme precision spectroscopy. Now, this is a story of technology development. So extreme precision spectroscopy is a measurement method that we use. And its trajectory was driven by a science question, that of catching dancing stars. Now, to catch a dancing star, you might say is kind of vague, sounds a little bit poetic. So let me ground that in a little bit more physics language for you. So really what we're talking about is to measure the movements of stars. Now, our story begins in the 1500s. Astronomy, of course, is an ancient art. People have been looking to the heavens almost as long as there has been humanity. But this is still about 500 years ago. We're still in early astronomy. Now, these early observations of astronomy mostly related to measuring the motions of planets. So when our ancestors looked up to the skies, they observed what looked like a fixed grid of stars and moving planets against them, which is why planets were called planets or wandering stars. Now, to them, the stars were merely fixed points of reference, and it aided them to measure things like the planets, the moon, and the sun that were moving on much faster timescales. This outlook continued into the early 1700s. And so if you had asked an astronomer of this time if the stars were truly fixed, they might have hypothesized that these might be moving bodies, but this was all theoretical because in reality, these motions were too small to detect. And so people looked at the skies and did not expect them to change very much. However, Edmund Halley, famous for the comet that's named after him, was perhaps the first to discover that some of the stars in the sky actually seemed to be moving with respect to other stars. They were shifting their positions in the sky. In 1718, he announced that several well-known bright stars that were observed with the naked eye from much before then, Sirius, Aldebaran, Betelgeuse, Arcturus, these seemed to be in different positions than they had been in Ptolemy's catalog. Now, Ptolemy's catalog was an ancient one recorded before the birth of Christ. And this was the first time that astronomers realized that the stars were moving perhaps very slowly against other stars that were further away. Now, the observations of these motions of stars progressed very slowly at first, just because there were no good records from the ancient times to compare against. And so it was hard to tell if the stars had really moved or if there was errors in the records. There were measurement errors that made it seem like the stars were moving. However, over the next decades, this science of measuring the positions of stars in the sky, also called astrometry or celestial cartography, mapping the stars, grew to encompass all of the nearby bright stars. And so you'll see in these call-outs below, in about the 1760s, there was a remarkable catalog created by an astronomer called Bradley at the Greenwich Observatory in the UK that had over 1,000 stars, measurements of over 1,000 stars. And for a lot of work, this is sort of the oldest anchoring point for the positions of stars. In the 1880s, Pickering at Harvard was a famous astronomer who started measuring the positions and colors of stars and published a catalog called Harvard Photometry that had 4,000 stars. This work continued into the 1918s and the 1920s when the Henry Draper catalog was produced. And this is a catalog and classification that we still use, compiled by the very famous Annie Jump Cannon, who also came up with a stellar classification system. And then on to the 1930s, when there was a Yale Bright Star catalog that cataloged about 33,000 stars. And so several catalogs were starting to record the shifting positions of the stars on the celestial sphere. And this shift across over time, which really marked speed is distance over time, this was named their proper motion. Now, proper motion is useful to understand what is happening in the universe, but by itself, it provides an incomplete picture. And this is because proper motion only marks movement across the plane of the sky, but in reality, stars are moving in arbitrary directions. And so they have some component of motion that is going away from us or towards us, so along our line of sight. And so to truly understand the star's motion in space, we also need to know whether it is moving towards or away from us. And so you'll see here in this illustration that the proper motion is against the plane of the sky. but it does not tell you anything about what we call the radial velocity. So this motion along the line of sight is called the radial velocity. And clearly, this is an important piece of the stellar puzzle to really understand how the stars are moving in 3 dimensions in space. But how can it be measured? This was a question that was still unanswered in these early times. It could not be measured the old-fashioned way by taking images of stars or drawing maps of the positions of stars on the sky, because the line of sight motion does not change the positions of stars on the celestial sphere. I might also ask you at this point how on Earth you would measure if something was moving towards you or away from you. And you might say that you'd look at the size of the object, right? The object would get bigger as it got closer and smaller as it got further away. But stars are so very, very far away that they are not resolved objects where we can see their size. So they're always pinpoints of light. And so we definitely cannot measure the changes in their sizes if we cannot measure their sizes at all with imaging. And so we turn now to a different phenomena. We're going to move away from stellar mapping and learn about a phenomena called the Doppler effect. Now, at this point in the 1700s and the early 1800s, the Doppler effect was just being discovered. So it was discovered by Christian Doppler in 1842. And essentially what he discovered is that when a source of light has relative motion towards you, it appears a little bit bluer than it originally was. And when it's moving away from you, it appears a little bit redder. And the way to understand this is shown in the diagram below here, where if the source is moving towards you, then every consecutive wave of light seems to come a little bit quicker. And so the frequency of the light seems to go up. Whereas if the source is moving away from you, you can imagine each light, the crest of every light wave takes a little bit longer to arrive. And so it looks like the light wave is being stretched out, which changes the frequency of the light, and it can appear redder. None of this, of course, is visible by our eyes. These are very, very small changes in the frequency of light. And so even though there are slight blue and red shifts, this is not something one can look at the stars and observe. And so one needs newer tools than just our eyes. And this is where we begin to talk about spectroscopy. So to study the spectra of the stars is to look at the detail in the light from the stars. When the light from a star is passed through a dispersing element, say a prism or a grating, it gets dispersed into its constituent colors, much like a rainbow is formed. And these colors of light tell us what the star is made of and can tell us actually a lot about the history and formation of the star and how old it is and where it might be going in its lifetime. So the first analysis of stellar spectra was conducted in about 1817 by an astronomer called Fraunhofer, who looked at the spectra of the sun and some of the brighter stars and noticed that these were not continuous rainbows of light, but that they were punctuated by what he called absorption lines. So there were dark regions in the spectrum where the light had been absorbed by something else. And so Fraunhofer empirically, by looking at it, classified hundreds of solar absorption lines. And this was very much in line with understanding that was emerging at the time in physics, that hot gases emitted certain wavelengths of light. And conversely, those gases, when they were cool, could absorb those same wavelengths of light. And so Fraunhofer, along with several of his contemporaries like Bunsen, of the Bunsen lamp fame, were able to show that the missing lines in the stellar spectrum corresponded to the stellar atmosphere composition. So the cooler gases in the stellar atmosphere were absorbing certain components and leaving a fingerprint on the spectrum of what the star was made of. And so this was our first view of what distant objects like stars were actually made of, including the sun. And so to study these spectra, people used very early spectrographs, which were quite simple. They were essentially made of a prism and a few lenses to guide the light in and out of the prism. But what even very early spectrographs did was take colors of light and translate them to different positions on a photographic plate. And so now color corresponded to position on a photographic plate, and you could track the motion of different lines on those photographic plates. So this was a brilliant way of converting something that we could not see, the very subtle change in the colors of stars, to something we could see, the movement of these dark absorption bands on the photographic plates. So let me show you what some of these early photographic plates looked like. Imagine yourself as an astronomer in the 1800s, pointing your telescope and your early spectrograph at an unknown object and seeing what light and what photons were coming from these distant stars. It's really quite amazing. The first radial velocity observations of stars using photographic plates were taken almost 150 years ago from now in 1872. And the astronomer who discovered or conducted these first observations, Vogel, along with Pickering, who I mentioned as one of the catalog creators, also discovered the first binary stars. And they did that because they tracked the changes in these absorption lines over time and saw that they were moving back and forth around a rest wavelength, which indicated that the star itself was moving back and forth, red shifting and blue shifting over time, and that this wobble was being caused by a companion whose gravitational energy was wobbling the star. And using the already discovered astronomical and physics laws of those times, they were able to measure the masses of the companions, or guess at the masses of the companions, and tell that those were also stars. And so measuring the radial velocities of stars led to the discovery of binary stars, the very first binary stars. Now, I will say that these early measuring machines were very cumbersome to use. Astronomy currently is not a hugely physically taxing career, but it could be at that time. And so here's a picture of one of these early machines where one had to look through a microscope and manually move a micrometer screw in precision steps to try and measure the movements in these lines, because they were still moving by very, very small amounts. And so you had to look at it very, very carefully to measure it. And the papers of the 1940s mentioned how the fancy updates of the time added a projector to this setup so that you could project the spectrum onto a wall so that it was much larger. And now you could move a screw against it with your naked eye. And this relieved the extreme eye strain that graduate students were undergoing in trying to measure these spectra. It's also interesting to read about how knowingly biased these observations used to be, because every astronomer kind of had a technique for measuring the shifts, and they always tend to either veer a little bit to the left or the right, depending on the astronomer. And so a lot of the advice of this time says that you should pass through the spectrum one way, going left to right, and then the other time going right to left. So you kind of cancel out your own bias. Very interesting how they were already thinking about these things, but of course, a far cry from how we would address these problems now. Here's some early spectra measured from that machine that I just showed you. And so always when they were measuring the shifts in these absorption lines, you had to measure it with respect to something else. So you needed a reference spectrum for comparison. And here you'll see there are these more continuous looking spectra are from the stars. So there are 1, 2, 3, 4, 5, 6 stars here. But along with the stars, they observe a reference spectrum from an iron arc lamp. So these are emission lines from superheated iron. And these lines are at known wavelengths. And so using that, you can basically create a ruler against which to measure the changes in the spectrum lines. This is quite old technology from the 1940s, but this principle is still what we use now, where we have a reference spectrum and we measure shifts against it. So in reading some of these historic papers, it's very interesting how some of the technology was in a very early state, but how a lot of the thinking was already in a very mature state, and still some of the principles that we use today. So these early measurements of the radial velocity of stars led to some really amazing insights into the nearby universe. So the motion of the sun, for example, was measured for the first time. Before that, again, the sun seemed like it was a stationary object as far as we could tell from just looking at the sky. So without the spectra and without these measurements, these small motions are not apparent at all. Also, very interestingly, the sun and the nearby stars seem to be in slow revolution around a distant point in the galaxy. So this is sort of foreshadowing a lot of the astronomy that will come in the centuries after this, where we discovered the center of the galaxy has a black hole, and all of the stars are sort of rotating around that center. Also, extremely distant spiral nebulae, so these are what we would now call other galaxies, seem to be redshifted more and more depending on how far away they were. So again, this is a very early indication of later discoveries of the expansion of the universe. But you can imagine this is the first time astronomers were really being able to look out with this level of insight into what was going on. So we are now in the early 1950s. Historically, we are at an interesting moment in time where the Second World War is over, the Cold War is dawning, the civil rights movements in the United States is picking up pace. Just to remind ourselves that alongside the story of other human history, there is also the story of science developing. So this is still a time before exoplanets. The only known planets are those in the solar system. And the idea of alien worlds only exists in science fiction. However, in the world of astronomy, a scientist called Otto Struve writes one of the most prescient papers in the field. He says, we can already detect radial velocity shifts due to stellar companions, right? We know about binary stars. If we increase our precision, we should be able to detect smaller objects, smaller companions. And so if there are close-in planetary companions, these should be within our reach. Of course, with the caveat if they exist, because there was still no proof that planets existed outside the solar system. This was quite a revolutionary idea, but it would still take decades for technology to catch up to this visionary idea that Struve had in this time. So this idea of developing precision spectroscopy comes from the principle that the planet is causing the star to wobble, and both of these bodies are orbiting a common center of mass. So just to center our discussion, I wanted to show you what this looks like, where the planet, being small, is making a large orbit around the star. The star, being very large, makes a very small orbit around the center of mass. And the motion of the star back and forth causes the spectrum to redshift and blue shift. And those are the motions we're looking for. However, the problem between Otto Struve's idea and the actual realization of it was just how challenging this measurement can be. So here we are at the beginning of the journey in the 1950s, where RV precision is at about 1,000 meters per second, so about a kilometer per second. This is the precision at which you can discover stars, companion stars. But to get to planets, you need to get orders of magnitude better. So Jupiter, for example, wobbles our sun by about 13 meters per second. And the Earth wobbles our sun by only about 10 centimeters per second. So you'll see on the y-axis here, these are jumps in magnitudes of 10. And so we need to make 1, 2, 3, 4 jumps. So we need to get 4 orders of magnitude better to start finding Earth-like planets. No big deal, right? 4 or 10,000 times better. And so this is what the monumental challenge that lay ahead of astronomers of the time, where we needed to get technology to a place that really couldn't even be imagined at the time. So there was a lot of skepticism going around. People were saying this is an impossible task. 10 centimeters per second, that is very, very slow. That's slower than a person walks. It's about the speed of a tortoise. And so you're trying to measure the motion of a tortoise light years away. That's impossibly difficult. And so a lot of people believe that finding planets would always stay in the realm of science fiction, that it would never be something we could actually discover with technology. However, some intrepid scientists kept trying. And so we jump ahead to the late 1970s, where a pair of astronomers, Campbell and Walker, did a very daring experiment using perhaps some of the most dangerous substances that have been used in this field of astronomy ever. And so they had this idea of using a calibrator, say a ruler, that is imposed onto the stellar spectrum. And so what they did was that they passed starlight through a hydrogen fluoride absorption cell to imprint the absorption lines of hydrogen fluoride onto the stellar spectrum. There had also been a lot of advances in detector technology by this time, making this experiment much more successful than any of the ones that had gone before it. And so Campbell and Walker were able to get to something like 15 meters per second precision, quite a bit better than the several hundred or 1,000 meter per second precision that came before them. Of course, the problem, which is sort of understated in their published paper, is that a drawback to hydrogen fluoride is its obnoxious nature. What they don't mention is it's horribly toxic, and even a little bit of HF on your skin or in your lungs can prove fatal. And so while this experiment was successful, this was probably not the most feasible of solutions. But what they had demonstrated was that an absorption cell with the right number of lines and in the right wavelength range might prove to be a great solution. So let's jump ahead to the early 90s, so about a decade after the Campbell and Walker experiments. And by this time, there have been some hints of substellar companions, but still no definitive planets. And two groups in two different continents are racing to be the first to find an exoplanet. So stateside, there is a group in California. They've been building on this absorption cell idea, and over many iterations have been looking for the best filler gas for the absorption cell. And they have settled on iodine, which has some very nice lines in the optical part of the spectrum. And they're using that at Lick Observatory to study many, many stars and track them over time to see if there are planetary companions. Across the pond in Switzerland, actually the observatory is in France, but the group is Swiss. There is a group that is going a different route. So instead of imprinting the ruler onto their starlight, they are still doing a simultaneous measurement, sort of like the ones I showed you before, where they're measured at the same time, but next to each other, so not on top of each other. And this group is using a thorium-argon lamp for its calibration. But the reason they are sort of decades ahead of the last experiments is that they're using a stabilized spectrograph. So the spectrograph itself is built to be somewhat immune to temperature and pressure changes so that those spectra next to each other don't suffer very different systematics. And so a lot of exciting work happens behind the scenes with these two groups. But what the world sees is an announcement in 1995 of the first exoplanet around a sun-like star. So in 1995, the Swiss group, Mayer and Quillo, announced the discovery of 51 Peg B. And actually the California group perhaps already had that discovery in their data, but they were able to verify it almost immediately. But the first exoplanet that we found was unlike anything that was expected based on the solar system planets. This planet was what we now call a hot Jupiter, so a very large planet, actually larger than Jupiter, that was very close to its star, much closer than Mercury in the solar system. And this giant hot planet was whipping around its star every 4 days. This was unlike anything we had expected or seen before. And with this staggering discovery, the field of exoplanet detection was born. And I'll show you what the state-of-the-art data looked at the time. If you look at the plot here on the top right, these are the measurements that were taken over time of 51 Peg B. you can imagine time on the x-axis, and this is radial velocity in meters per second on the y-axis. And you can see very clearly that the star is shifting to the red and the blue, and the red and the blue again in this beautiful periodic sinusoidal curve that shows us that there is a companion, and the size of the curve gives us the mass of the companion, essentially. And so it tells us that the companion is smaller than a star, much smaller. It's a planet. And so we've made great strides in precision now from the early 1940s to the 1990s. We are now in the middle of our journey of this 4 orders of magnitude, 10,000 times that we're trying to get better. So we started off at the speed of detecting the fastest military aircraft at about 1 kilometer per second. We traversed through high-speed trains and very fast runners. And we are now getting to about the average jogger. So still a little bit faster than you would walk at several meters per second. The next challenge after this was getting to 1 meter per second. And the Swiss team that I mentioned grew in both expertise and number of instruments that they were producing. And they produced in the 2000s the state of the art and held that distinction, actually still hold that distinction as the team that has gotten to the highest precisions on any instruments. And so HARPS defined the state of the art in the 2000s and the 2010s. This is the instrument on the left here. You can see this is a lot fancier than those cranking micrometer instruments we saw before. These are highly stabilized instruments in a vacuum chamber that have large optics and very high dispersion. So they cover a large wavelength range of light, and they spread it out very finely so that you can see the detail in the spectral lines. And so the simultaneous measurement technique slowly bypasses the absorption cell technique and becomes the mainstay of the field. It can cover a very broad wavelength range. And it is proving very successful. We are finding hundreds to thousands of planets with the radial velocity technique, but we are still at this point stuck at about 1 meter per second. So Earths, which are at 10 centimeters per second, are still beyond the reach of this technology. And so we've taken one more step here in our journey to precision. We are now at a casual walk at about 1 meter per second, but still about 10 times less precise than we need to be for Earth. So how do we get better from here? In the early 2010s, technology was already maxed out. We were using the state of the art. And so the community sort of rose to the challenge. We decided we would forge our own technology and drive forward the areas that needed to be improved. And to do this, we looked at every possible source of error that could be detracting from RV precision. So starlight traveling from the star through Earth's atmosphere, through the telescope to the instrument, anything along that light path can add errors. And so we have to think about everything that the light encounters and how to control it so that it doesn't create fake shifts in the data. This is about also where I started my career in exoplanets, thinking about what the errors were and how to solve them. So here I'll show you what we call an error budget. So it is a systems engineering tool for describing all of the errors that we think are possible and trying to put some bounds on them. Lots of these are actually very difficult to understand or measure. And so you'll see they're color coded by our confidence in them. But we don't need to go into the details, but I do want to show you sort of some of the spheres of concerns that we have. So here is the main instrument, and it has a lot of thermal stability concerns. So we're trying to make it as mechanically stable as possible and not reactive to temperature changes. There is the detector itself, which records the incidence of photons on it. Of course, you can imagine lots of errors creeping in there. And so we have to worry about things like the shapes and the sizes of pixels, the thermal response of the detector, etc. We also worry about transporting the light from the telescope to the instrument. So we use optical fibers to do that. And so there are several error terms that can crop up while the light is traveling. And then there are some external errors like the telescope. The telescope might shake from the wind, or we might not be focusing on the star just right. Those are all things we worry about and try to control as well as possible. And lastly, there are atmospheric effects like clouds passing by, or a particularly humid night. All of these affect the light as it travels through. There is another major error term here, which is the star itself, but it's not in this chart because we have no control over it. And so all we can do there is to try to understand the star and correct those in post-processing. You'll also see there are boxes here for software because at this point, software or your analysis technique is just as important as your hardware. And if you're not careful, you can introduce errors in your analysis. And so with all of those worries in place, we embark on building these next generation of instruments that will hopefully take us closer to Earth-like planets. And so the overarching philosophy for these instruments is that we are going to stabilize everything possible in hardware. So these are built to be some of the most stable pieces of equipment in the world. They are stable to a thousandth of a degree in temperature. And once we stabilize everything in hardware, we don't expect it still to be perfect. We are then prepared to correct everything that's left in software. So we put in as much effort into the software as the hardware. So let me show you a few examples of the advances that we've made. We don't have time to go over all of it, but I'll show you some of the highlights and pretty pictures of how we advance the field. So one of the things we worry about is something called fiber modal noise. It's basically an interference pattern that arises as the light travels through the fiber. And so this is an extreme case that I'm showing you. If there is a single wavelength of light going through a fiber, you see the worst case of interference. And so you see this terrible speckly pattern. And you can imagine if you're trying to measure motions from a planet that would wobble a star, that would show up as very small changes in the centroid of the light, so the center point of the light. And this kind of speckling just overwhelms that. You can't see the planet at all you see is noise from the fiber. And so as a grad student, I designed something called a modal noise agitator. The funny story that goes with this is that this was actually a mechanical design based on how us graduate students were wiggling the fiber, which seemed to work the best. And so we had an engineer try and mimic that exact same motion. So this is a mechanical grad student trying to agitate the fiber in exactly the same way. And you'll see on the right here the effect of doing that. So with the same setup, just with the modal noise agitator, you'll see that the illumination that we get out of the fiber is very, very smooth compared to before. And it's essentially smooth enough that now you could measure the effect of a planet instead of being overwhelmed by noise. So this is one noise source in our list of tens of noise sources that is now retired. So it's not a problem anymore. Here's another one. So this has to do with the interface of the telescope and the fibers. So the telescope tries to focus the light onto the fiber, but because it cannot do it perfectly, sometimes the star can wander on the face of the fiber. And if you are not careful, that can change the output that goes into the instrument and therefore the wobble that you measure. So it creates a fake wobble where there isn't one. And so here again, I spent several years actually of graduate school time developing this technology to scramble the light. And so this is called a ball length scrambler. It's essentially a tiny 2 millimeter ball in this case that is in the path of the fibers. And given the composition of the ball and the alignment of this part, it basically scrambles the light, removes any memory of the input illumination. And now no matter where the star is on your fiber, in this very extreme scenario, I'm moving the star all the way from one end to the other end of the fiber. Usually the telescope does a better job, but no matter where it is, the output illumination is perfectly stable. And so this bottom picture is actually also a movie, but you can see that by eye, it doesn't seem to be moving at all. And so this is another error term that we were able to retire. Other ways we increase stability. So we design a new level of thermomechanical stability. So that means mechanical responses to changes in temperature and pressure. This is the habitable zone planet finder spectrograph, showing what's inside the huge vacuum tank. And this whole system is kept very, very stable. So you'll see here how an instrument called NUID, another one of these, compares to HARPS, which was the previous state of the art. So it's about 2 orders of magnitude more stable in temperature, and 1, 2, 3, 4, 5 orders of magnitude more stable in pressure. So we're doing our best to provide a very calm environment for this instrument. We also designed a new level of optical stability. So this is an instrument called the Keck Planet Finder. And here is a beam of light traveling through the optics of that system. This design itself is not very new. It's actually been in use for several decades, but the implementation of it is much more careful than ever before. And so we do our best to avoid errors that can arise while the light is traveling through the instrument itself. And lastly, once your detector records the photons and you have your data, then you move to analysis. So we also have to design, like I said before, a new level of algorithmic stability. So again, software and data analysis is just as important as the hardware here. And so we have to design precision analysis software. I'll also show you what the data looks like now compared to those photographic plates. So we've come a long way. These are really beautiful records of the stellar spectrum. You'll see here in the zoomed in regions, the starlight is this sort of continuum looking light again with the absorption lines. And you'll see this beautiful trace of dots next to it, which is from something called a laser frequency comb. So this is the newest and best version of a ruler that is available now. So moving away from the absorption lamps, the emission lamps, we now have this laser frequency comb, which in itself is actually Nobel Prize-winning technology and much more complex than our spectrograph. But it provides a ruler that is tied to the atomic standard and just way more precision than we actually need. So it's a beautiful reference to calibrate against. So we are just finishing building this new generation of extreme precision spectrographs, and these are called extreme precision because they are the last step in that progression of precision that I was showing you. And for the first time in history, we are now close to detecting true Earth-like planets. And so here is our last step that we have just taken from the casual walk level to that of the tortoise, which we have been aiming for. And while we are not at 10 centimeters per second yet, we are at about 30 centimeters per second and getting closer to 10 centimeters per second. Some of that gap can actually be closed with algorithmic work and not necessarily new instruments. And so there is a lot of work to be done in this field as these new instruments come online and give us, again, a new view of the universe, just as those first spectrographs did. And so just to show you that some of these instruments are actually on sky, this is an instrument called NUID, one of several instruments that I built, and it is observing right now at Kitt Peak Observatory in Arizona. And every night it's looking for planets, and during the day it actually observes the sun so that we can understand the sun better, but also understand our instrument better because the sun is a relatively well-known star. And we're polishing a lot of our analysis techniques on data of the sun before we apply it to the stars. And so this is science advancements that are happening right now. And so that is mostly where the story ends, but I will leave you with the teaser trailer for the next part of this story, which is that at this level of precision, we have overcome all of the instrumental barriers. And so it turns out that at this point, our new nemesis is the host stars themselves. And so in the sequel to this story that you'll have to wait for is how stars hide real planets and can pretend to have fake planets. That's all from me. Thank you so much for listening, and I'll turn it back over to Frank.
Oh, thank you, Arpita. That is quite the journey from noticing different stellar movements between old catalogs of stars that you couldn't verify over the course of 1,000 years, down to finding, that tiny little motion, and getting down to 30 centimeters per second has been quite the journey. It's kind of fun because I've followed this from a distance, being somebody who's not in the game, but really followed the just the enjoyment of seeing how things are pushed down. I was at Berkeley, actually worked with the team with some of their iodine things. I didn't do anything on the team for the exoplanets, but I was a computer geek, so I was able to help them improve their software processing back in the 90s.
That's really cool, Frank, because I think a lot of the challenges even then had to do with processing the data.
Right. Yeah. And getting a new machine, and running it on a new machine just totally speeded up things, or just using a different compiler actually sometimes. Yeah. All right. So we got about 150 people watching online here, and they had a bunch of questions. You got a lot of compliments, by the way, on the clarity of your presentation. I just want to let you know that they really enjoyed the fact that how carefully you worked through this. But we had an interesting question because you mentioned that they were able to start measuring the sun's motion. And one person sat there and said, all right, so the sun orbits the galaxy. Does that mean it moves from spiral arm to spiral arm? What's that motion that we've measured here? What's that all about?
Yeah, that's a great question. So the sun they found was moving, but also the nearby stars were moving with the sun. They were all moving together. And so the sun is not moving away from its neighbors, it's moving with its neighbors. And those are the other stars that make up the spiral arm. So it turns out the whole spiral arm is moving, and the galaxy sort of retains its shape, but the whole of it is rotating.
Okay, and sun's moving at what's do you remember the current velocity that we know what the sun's motion is?
In the galaxy, I don't.
Okay.
About 300 meters per second, I think.
Yeah, so it's been over my career, it's been down about 200 and as high as 250, 300 or something like that. Okay. All right, and that's actually kind of interesting to note that it takes a couple 100 million years for the sun to orbit the galaxy once, too. All right, so Grant Justice has been following the questions along with me in the YouTube chat. Grant, do you want to join in and ask some of your favorite questions from the chat?
Yeah, absolutely. We've had a good audience, and I have to say, like, most of the questions I've seen in the chat so far have been answered by the presentation. So excellent job, Dr. Roy. All right. The first one off, I like this. How is your work going to be affected by JWST coming online? And then after, if we get to the Roman, what do you see the future of your work with the new instrumentation coming online?
Yeah, that's a great question, and something I think the whole field is thinking about now. So this technique of measuring the masses of planets will continue to be useful, but we're always trying to push our instruments to do a little bit more. And so now that we're sort of able to routinely measure small planet masses, one thing I'm really interested in is studying exoplanet atmospheres with these instruments. And so there is a very challenging, but a small path forward in directly trying to measure planetary photons while measuring the stellar spectra. But that is a incredibly difficult way of measuring stellar atmospheres. There are actually slightly, well, not easier, but different ways, like building a $10 billion space telescope and sending it to L2. And so JWST will also study planetary atmospheres via the transit technique. So it will look at the difference between stars that have planets in front of them and stars that don't. and
This was
thereby
going to be another question from the chat. So if you want to elaborate a little bit
Sure.
more about how you can actually tell the atmosphere and how precise the instruments have to be in order for you to get that sort of a determination. That was another question I was going to ask. You just phased right into it.
Great. So that question was about JWST or just in general?
More of a general statement. How do you
Okay.
get the accuracy necessary to view atmospheres and composition in addition to like what it can do for your work with the new telescopes? I'm just kind of piggybacking
Yeah.
here.
Yes. Yes. Okay, great. Right. So in studying atmospheres, JWST will study atmospheres. Roman will try and study atmospheres. And so really all of these instruments are telling different chapters of the same story. And so to understand a planetary system really holistically, we need all of these pieces. We need to understand the star. We need to understand the size of the planet, the mass of the planet, the composition of the planet, the atmosphere of the planet. And so these are all sort of patchwork parts of the same story.
Okay, so let me break in here. Let me just break in here. So just to answer one question, right? You said that JWST will use the transit method, but JWST will not be using the radial velocity method, which is what you focused on here. And I presume it's because you don't have astronauts up there to wiggle the fibers, you know?
Yeah, so we actually don't fly any radial velocity measurement instruments because they need to be so stable. And right now, at least the technology that we have is also very large and heavy. And so there are also people trying to build smaller versions of these that could be flown in the future, but we cannot do precision spectroscopy from space right now.
So great. So that establishes an answer to one of the things is that radial velocity technique is actually best from the ground.
That's right.
But you still have to deal with the atmospheric distortions.
That's right.
And if we could get it into space, we could do it. But right now, that's not technologically feasible. Great.
Right. So there actually is a couple of teams working on making these smaller versions where the whole argument is that we're above the atmosphere, and so we don't have to worry about what we call telluric lines from the atmosphere.
Right.
But there is still, I think, some gaps there in space technology and in managing stability and focusing on the star, etc. Okay, I'm trying to answer a lot of questions.
Okay, no. Then that's why we're interrupting and pausing and making sure.
Yes. Thank you for picking out the threads.
Pick out the threads. All right.
Right.
So,
okay.
What's the next thing? Is it discussing the transiting method, or what's the next thing she needs?
Yeah. So let me talk about atmospheres from both of these points of view. So with spectroscopy and then with transits, which is what we call photometry. Which is so not spreading out the light, but just looking at a small range of wavelengths of light together. So in the transit method, of course, you're lucky enough that the planet is passing in front of the star from your point of view. And so it's basically blocking a part of the star for a short part of the time and then going behind the star. And so you could take, this is more like the imaging that I was talking about early on in astronomy, where you can take essentially an image when the planet is in front of the star and an image when the planet is behind the star. And the difference between those gives you the effect of the planet, right? How is planet plus star versus just star? And that difference comes from the little bit of starlight that passes through the limb of the planet's atmosphere and picks up a little bit of the signature of the planet's atmospheric composition. And so that is a very nifty way really to try and study the planet's atmosphere, and has been very successful. And that's what JWST will do as well.
It seems very roundabout coming from the outside, though, catching the little lip of the planet and the transit. Yeah. Right.
And so, so let's think about a more straightforward way to do that. How would you look at the light from a planet? You would take a picture of the planet, right? And so that has been very challenging because stars are very bright. And so if you take a picture, all you see is the star and not the planet. And that's where Roman comes in. And so Roman will have the technology to try and block out the light from the star, kind of like shading your eyes from sunlight to see, things that are close to the sun in the sky. And so by blocking out the starlight, we will be able to see a little bit of light from the planet and directly image the planet itself. This is still difficult to do even with Roman for close-in planets. So Earth-like planets are still too close. They're overwhelmed by starlight. But you can get planets that are further out, or planets that are hot themselves and have a little bit of their own light. Right. Those are the ones you can study.
And that's important to do that in the infrared because the planets glow brightest in the infrared.
That's right. Yeah, the hot young planets are bright in the infrared.
Right. So, I mean, one of the reasons why JWST is going to be such an exoplanet machine is because if you're Hubble could look at planets, but they aren't bright in the visible. You really want to get the brightness coming from them. You're going to need the JWST.
That's right. That's
get the infrared light.
But then there is a third and very new way of studying planetary atmospheres with these extreme precision spectrographs that I use. And there, instead of trying to separate the planet and the star spatially, which is what imaging does, or waiting for a transit to happen, you separate them in velocity space, because we're all about looking at the shifting spectra. And so the planet and the star move differently. When the planet is moving towards you, the star is moving away from you, and vice versa. And so they separate out in their blue shift and red shift. And so really, when you look at this system, you're getting a lot of photons from the star, 10 billion photons from the star, and 1 photon from the planet. But you are getting that 1 photon from the planet. And so if you observe for long enough, you can try to build up that planetary contribution and disentangle them by their motion. It's very challenging. It hasn't been done. I'm trying really hard to do it right now. But again, I'm trying to do it in the optical. It's a little bit easier in the near infrared, especially if the planet is bright there. And so it has been done in the near infrared for a handful of planets, even non-transiting planets. So this is one of the only ways to study the atmospheres of non-transiting planets. So yeah, there's a lot of exciting atmospheric work coming up.
Yeah, and it is as I've presented to kids that when I grew up, we had Star Trek that was going around exploring other planetary systems, and now the kids growing up these days, they get to explore them for real. Unfortunately, they just don't get to go there. They can explore them by these things, and to have that come to life in my lifetime is really wonderful. Because we've got 4,000 planetary systems out there that we know about.
That's right. I think the thing that still blows my mind is that when you look up at the night sky, a lot of the stars that you see, maybe most of the stars that you see, have planets, and maybe habitable planets, which kind of makes it all seem very close.
All right. So one person obviously thinks about media delivery, says your modal noise actuator could help the fiber internet delivery to improve its signal to noise ratio. But can you figure out how to wiggle fibers that they're buried underground?
Yeah. So actually the telecom industry is far ahead of us in thinking about fibers. And yeah, I think there are already modal noise solutions for those fibers. So since we built that modal noise agitator, which was a few years ago now, you can now buy just tiny off-the-shelf parts that will very softly squeeze and wiggle the fiber. Because the less you wiggle it, the less you damage the fiber also. So you don't want to go swinging it around too much. But you can buy agitators that are really small. And so we did patent the scrambler. We probably should have patented the agitator as well.
But astronomers are generally not in it for the money. Unfortunately, we don't think like that.
Yeah.
Grant.
Thank you for bearing with me on the deluge of questions, but they were all loosely related, and I needed you to bring them together for both me and the audience. Yeah. All right, so I'm going to take a slight departure from the science here, and a lot of the audience is very interested in you because you are very knowledgeable and have given such a good talk. Why don't you talk a little bit about what got you interested into this and a little bit of your journey into astronomy?
Sure. So I was always interested in astronomy, and so without quite knowing what it meant to be an astronomer, I think I was, taking classes in undergrad and trying to get closer to professional astronomy to see what it might be like. And I remember I decided to take a gap year after undergrad to think about whether to go to grad school, since that can be a bit of a commitment. And I spent that year at Penn State, where they had just started this Center for Exoplanets and Habitable Worlds. And I had never studied exoplanets before. In undergrad, I worked on gravitational waves, which, were still in the pre-discovery era. So everyone was racing to find gravitational waves. And exoplanets, I feel like I just took to it very naturally. Exoplanets are so much easier to get excited about than some of the more obtuse parts of astronomy, because I have an astronomy professor who said that these are other worlds. They remind us of our home, and we can imagine them, and we relate to them, and we care about them, and we like to we have so many stories about who else could be living on them and looking down on us. And so I think it's very easy to get excited about exoplanets and life in the universe. And I was lucky to join the field at a time when it was sort of exploding with activity and funding, which is important as a grad student, and new instruments to be built. And I think what I discovered is that I really enjoy making precision measurements. So, kind of digging down into the data to get that last bit of precision. And then seeing these tiny wobbles of stars that are light years away was just incredible. And so I've stayed in exoplanets and built several instruments since then. And I think this is maybe true of all astronomers, but the days when I can step back from the furious coding and think about what we're actually doing, it's still amazing to me that we can do it at all.
You may be drowning in Python, but you're discovering new worlds.
Right.
Yes. Arpita, I will say that you remind me of a lot of other astronomers in that you have a zeal for just basic problem solving. I think that error chart that you give, which, by the way, for the public, I just want to say that astronomers and scientists call it an error budget, but it's not really errors that we're making. It's just the uncertainty that's natural in it. Right. Okay. Yeah. Sometimes we do the public, they go, "Oh, you're planning on making errors." No. These are just uncertainties that are inherent in what we're doing. But in that chart, going through that and trying to solve each block of that, trying to come up with a way to address this problem. I see that in you, and it's kind of the thing that kind of drove me, but in a totally different way through astronomy. And I think a lot of astronomers are, a lot of scientists are just inherently problem solvers at heart. That's right.
And I think that's what makes being an astronomer not a really scary, intimidating thing, right? Because at the end of the day, the problems you solve are still small. There's just so many of them that they stack together and solve a big problem.
Okay. Grant, I am out of the questions that I had written down. How about you? Do you have any other questions for Arpita?
Absolutely. Do we have time for more than one, or I have a good one at least?
We might have time for two. Yeah, we could have time for two more.
Okay. All right. Well, I'm going to throw this one out there. This is a great question. What determines where to look in the universe? We've talked about this in other discussions before, but specifically for you, what is it that stands out to you that tells you, ooh, I want to look at this particular planet, this particular galaxy, this particular star? What calls to you in your work?
Yeah, that's a great question. So this actually is a really fundamental question to designing surveys for planet hunting, because what do we care about, right? So firstly, we care about nearby systems because there is maybe a shadow of a chance that we can send something there or eventually go there, right? So the closer it is, the easier it is for us to study. The more light we get from it, the easier it is for us to study. But another strategy that I really like, we canvas broader than this, but this subset of systems is very interesting, is other systems where Earth would be transiting to them. And so they are transiting to us and we're transiting to them. And so they are possibly studying us. And so in thinking about SETI or searches for any kinds of techno-signatures, we're calling them now, they're looking at us. And so it's interesting to think about what they would see. And therefore to think about the ones that we see in that context. So I really like to think about other beings checking our transit patterns all the time.
And could you mention a little bit about TESS? Because the Transiting Exoplanet Survey Satellite is sort of a precursor mission to find places that things like JWST or other missions might want to look at.
Just as a shameless plug before we begin, we have
Yeah, absolutely. I'm not averse to shameless plugs. Come on.
We have an entire public lecture about TESS. It's awesome. If there's anything in these discussions that you guys don't see or necessarily understand, or we don't get time to check or go into the questions, look at the public talks. Chances are we've talked about it before.
We have over 100 public talks on our YouTube channel.
It's true. When I was picking the topic, I kind of had to not pick some of the topics because there were already great talks on them.
Sorry.
Yeah. So TESS is fantastic. TESS is in the sky right now. TESS, in some ways, is a follow-up to the Kepler space mission, where Kepler was the first space mission to do transits at very, very high precision. But Kepler's strategy was to look at one patch of the sky for 5 years. And so to go really deep on some systems, on a patch of systems. There's hundreds of thousands of systems in there, but it's still a limited patch of sky. What TESS is doing is a little bit different, where it's scanning the whole sky, but not with the same baseline. So it comes back to the systems over and over again, but then it moves on from them. And so TESS is great for finding a lot of planets that Kepler never would have, because it didn't look in the sky in those regions. But in some ways, TESS doesn't go as deep, but it goes broader. And so it's a very different, but just as fruitful strategy. And so TESS is finding new planet candidates every day. And part of why we're building all of these extreme precision spectrographs, there's about, I didn't mention this, but there's about 23 new instruments on the ground coming up, that have been coming up in the last decade, is because we knew we were going to be rushed off our feet trying to follow up the TESS discoveries. And so TESS discoveries need to usually be confirmed. And so if you can measure the mass of it, you can be 100% sure it's a planet. And having the mass and the radius gives you some hint of composition, which is also very interesting. And so all these instruments are, again, working together to try and get a comprehensive view of the extrasolar systems.
Right. And yeah, we just want to make a point that, sometimes you have to do it in an entire mission just to get the candidates from which to follow up on other missions or other instruments and such. And so this is not something you do in the life of a graduate student. Okay, it's going to occupy a full career. You're not going to get out of this field.
Yes, that's right. And so all of the information that we have from TESS and Kepler and the ground-based spectrographs are all part of what goes into selecting targets for JWST and for Roman, and then eventually for the next great observatory, which will be either, I guess we're calling it LUVEX now, but it's really to be named. But that great mission in the future will basically try to be the defining point where we start looking for life, where we start taking images of Earth-like planets. So, I said we can't take images of planets yet, but we might be able to in the future. And this will sort of bring us full circle in astronomy in the story that I was telling, where we started by just looking at pictures of things and figuring out what was going on. And planets have been so far beyond our reach, but in the next few decades, we will be able to take, if we really want, we will be able to take images of Earth-like planets and study their atmospheres and really ask questions about biosignatures and habitability and be able to answer them, not just ask the questions. So there is quite a tremendous arc ahead for this field.
Absolutely.
One of the ways I like to think about TESS, just more as a layperson, is TESS is kind of like a spotter. Like, it's not going to actually do whatever it is or do the science or look hard at it, but it's just saying, hey, there's a star over there. We should look at it. Like, it's a candidate. Yeah. It's kind of scouting it out ahead of time.
That's
and that's cool. I genuinely didn't know that many installations were coming online with instruments. That's wild. All right, this is a good question to end on. I like this.
Let's go for it.
Yep. How have you found your collaboration, like, across the world on this sort of stuff? Do you work often with other teams who are outside of the US, the EU, that sort of thing? Like, talk a little bit about, like, the multinational, like, world scale of the science being done.
Yeah, that's a great question. I have had a fantastic experience with the RV community. That we are spread out around the world. So there's a lot of activity in the US. There's a lot in Europe. There's some in India. I'm part of a team there. There's some in South Africa. There's some in China now. Yeah, it is absolutely a global effort. And actually, this field, the radial velocity field, does have a history of a more contentious atmosphere, because the stakes were high and people were kind of competing to claim these first planets. But turns out there's plenty of planets to go around, and so people are much more open and share, from software to hardware to secrets in figuring out the errors. And so I do collaborate with, and I'm part of several teams, some of which used to be kind of sworn enemies, but now work together just fine. And it's better for all of us because the challenges are the same, right? The data is complementary, and so everybody can help each other. And so I have really enjoyed being part of this field, and it really feels like a large scientific family where the stars are our nemesis or our friends and not each other.
That's great to hear, because sometimes you will see depictions in the media of scientists in these hard-pitched battles against each other. But the inherent nature of science as it progresses over the centuries is collaborative, right?
Yeah.
You stand on the shoulders of giants, and
Yes.
without many people attacking these really, really, really hard problems, you're not going to get a lot of solutions. First of all, and also you want there to be other teams so they can verify your results, because
Right.
if you put out a result and nobody can verify it, it just sits there, right?
Yeah.
And so the collaborative nature of science really was, the internet has totally transformed it and made it so much easier to work cross country. I mean, I've never met you, and yet here we are in this talk together, right?
Right. And I will say also, I was reading all these historic papers for this talk, and it used to be that one or two people would write a seminal paper, and that just never happens anymore, because we're at such a more challenging point that you can't just look at the sky and discover things. There's a lot of work that goes into it, and it takes a large team for every result. It's marginal advances at this point. I will also say, in terms of sort of teams that are publishing or checking your result, before I found a planet, I killed like several planets before I ever found one. And so that, again, can be a little bit contentious for the people who discovered those planets, but really it's the field self-correcting, right? It's like we have a little bit more information, we can understand better what's going on. And so now we kill off less planets within the field because we are more careful when we claim planets. And so,
okay. And just to clarify, killing a planet means saying, no, that detection
that wasn't real.
Isn't real.
Right.
Yeah. Okay.
Yes.
I was going to say, we're not
destroying any planets.
We
right.
don't have our own little Death Star that we can control.
That's right.
All right. Grant, any last comments from you?
No last comments. Everyone says thank you for the talk, and
all right.
Yeah.
Well, I will thank you again for the talk for our audience and for me. I will remind our audience that on March 1st, Hubble from space and integral field spectroscopy from the ground, seeing both the forests and the trees, Mark Sazi, Arma Observatory and Planetarium. Another talk that actually will show you the benefits of both ground-based and space-based. I got to say, we're at the Space Telescope Science Institute. We put forward the space telescope aspect of it, but it's always good to understand just how the space observatories and the ground-based observatories work together. And you'll hear more about it next time. Thank you all for watching.